I work with X-rays. And X-rays, they are something that most people have heard of because of going to the dentist, or if you break an arm, you have to go and take an X-ray. But X-rays, they are these very energetic particles that can actually penetrate our skin or bones and then make these pictures. But they are also generated in outer space. See, they are generated in very, very violent phenomena. For example, when a star explodes, or when clouds are moving, shock fronts, all sorts of things that are highly energetic. And the fun thing about the X-rays from space is that we cannot see them from Earth. So we have to send telescopes up outside the atmosphere.
Yeah, we can't see them from down here.
No. And that's a good thing, because
yeah, it actually is.
because otherwise we would have some damage, some radiation damage on the human beings here. So radiation is dangerous. That's why at the hospital you have all the safeties. But our atmosphere filters these X-rays. Yeah, the atmosphere has this protective function for us. And then what we do is we send the telescopes out in orbit in order to look out and find this energetic phenomena.
And it's all kinds of objects that can emit X-rays. It's from stars, galaxies, and phenomena on the sun, and so on. So, what kind of objects, phenomena do you research with your X-rays?
Yeah. So I don't like the smaller systems. So when I started studying, I wanted to understand the universe more in a broader scale. I had some philosophical thoughts about how things began and how things turned out to be this way. So I wanted to understand the evolution of the universe. And for that, we don't work with the smaller stars or the solar system. You would then work with really large scale, beyond galaxies. So my field of research is galaxy clusters. That means that they are the last part of structure formation. You would have the small things form first. You would have the first stars, then the first galaxies. And then when the galaxies clump together, you have the galaxy clusters. And in between the galaxies, you get part of this very primordial gas that is still cooling down, and it's sending X-rays. So that's my area of study. By looking at this gas in between the galaxies, we can tell something about what the universe is made of, how the universe is evolving, and how many things have happened in the universe so that we would get a system like that.
All right.
So that's what I got interested. But it is true that everything basically will shine in X-rays.
But you don't care about small things like galaxies, unless there are lots of them.
No. Actually, we can't even see the galaxies in my data. We can see the gas in between the galaxies.
Okay. So what have you found out?
Oh, we found so many things out. Well, I like to say that first, when we discovered these X-rays from outer space, we expected we would see it from the sun. And what you would do is you would send a rocket up in the atmosphere. It would be in the 50s. And then have a detector that would look at these X-rays. And then we had seen that the sun emitted also X-rays. The corona of the sun actually emits X-rays. But then we wanted to see the X-rays from the moon. And it's not that the moon is sending X-rays, but the moon is actually reflecting the X-rays from the sun. Yeah? So you would have a interaction there. But then when the probe was sent up to look at the moon, we actually found another thing shining in X-rays. And that was Riccardo Giacconi that observed that. He observed the first system outside our local environment here, which was the Scorpion X, which is the first X-ray source observed other than the sun. Yeah. But you see, you have to remember that the X-rays, looking out in X-rays, is something that started in the 50s, 60s. So for a decade, we had something like 10 hours of observations. While even the X-rays themselves are quite a recent knowledge. You have Røntgen, which is the German scientist that could identify the X-rays. He got the very first Nobel Prize, in 1901, I believe, something around that time. And 100 years later, we would then have Riccardo Giacconi win the Nobel Prize for his studies of the X-rays in space. But still a field that is quite young if you consider that Tycho Brahe was looking at the stars and measuring the angles between the stars. If you consider that Galileo was actually using a telescope and seeing the moons of Jupiter, X-rays are something relatively new.
It's a new phenomenon and a very extreme phenomenon.
And it's a very extreme phenomenon. And the technology that we need is also quite special because the X-rays, the light and X-ray energy, does not really work as the normal telescope. So you can't just build one big mirror.
Okay, so what kind of equipment do you need then?
Yeah, what we do at DTU Space.
All right.
So at DTU Space, we developed a technology which is, this is the very old type of technology that instead of making a big mirror like this, where you would have the rays coming in and getting reflected, you actually have to make a mirror that goes almost parallel to the rays. So the rays will come at a very low angle, we call it grazing angles, and then they will be able to be reflected in X-rays. So to do that, you need to develop the technology with these mirrors. You have to shape them in the right way, you have to put the right materials in, and then you put them all together. And then the telescope will have a very, very long focal length in order to focus this. So it's quite challenging to do this, but even worse, you have to do something like this that has to survive going to space.
Yeah, and so very, very long telescopes actually compared to lenses or mirrors and stuff like that we used to in the optical.
Exactly. For example, if we look at the Hubble telescope, it's quite compact. And even James Webb, you would have the system and the antenna, but it's quite compact. Like an X-ray telescope, this is XMM Newton, is an European X-ray mission, is a model, of course, it's not the real one.
It's a microsatellite.
Yeah, well, this is to scale, I don't know, but I would think almost like 100 times bigger. So this is the point where the light comes in, and then you would have this long focal length and the detectors would be out here. And for this particular system, we have 7.5 meters distance from the entry point.
7.5 meter long.
Yes. Yeah. So, this also poses a challenge of aligning and also sending the limits of how big the structure we can send to space. So this is the kind of things I do. So I started my education looking at the evolution of the universe. When we turned that into something very practical, it became looking at the gas in the galaxy clusters. And by the end of my PhD, I got the chance to come and join the team at DTU, developing the technology for the next X-ray telescopes. So XMM Newton was the telescope that flew a while ago. It flew in 1999, and I used the data of the XMM Newton for my PhD. But now I've been working with the next very large X-ray mission called New Athena.
New Athena?
New Athena.
Like the Greek goddess.
Like the Greek goddess. And when I got hired, they told me that I would see this mission fly in 24.
Oh,
and I was like,
that's right about now.
It's about now. The problem is that a couple of years later, I got hired at the end of 2010, and I said, 14 years to see this mission fly, it's a long time. But then a couple of years later, they said, well, a little more. Now we are in 24, and we still have 14 years to make it fly. So it will fly in the late 30s. But that shows also the complexity of sending a big space mission up.
So what will you be able to do with the new equipment once you got it? What will you be able to do science-wise? What can you see that you can't see now?
So the part that I love about it has to do with the clusters. There are two main science cases for this mission. One is to look at the gas in between the clusters, and they have now an equipment called the calorimeter that will allow us to observe the emission lines and the absorption lines of the elements in this gas. And with that, we can really tune the building blocks of what we are made of. We are all made of star powder. So we can see how many stars have evolved, have exploded in order to produce these elements
the
in the gas.
metals,
the heavy metals and also the more soft metals also. So that's one of the science cases, is really understanding the role of this of the gas in the production of matter. The other part would be how the black holes shape the universe that we have today. So seeing matter falling into black holes and how the evolution of the black holes actually shape our universe, and try to infer why things are the way they are.
Yeah. All right.
So it's the hot and energetic universe.
Going from parameters like temperature and density of the gas and so on, you will be able to look at the constituents and see how the elements are distributed and so on, and then also know about how the stars actually generated these elements and populated it.
Yeah.
But the black holes, I'm a little bit curious, because black holes are, you don't like small things, but black holes are singularities. You can't get any smaller.
Yeah.
So how does that compute?
Yeah, but that's the thing. So you're not looking into the black holes themselves, but you're gonna try to look at matter falling into the black holes, you see? And then something really special happens when you have, for example, a star, a binary system or something like that is actually falling into a black hole, being eaten. So you have those extreme conditions that will generate very high energetic phenomena.